Okay, so that's enough sort of surveying the landscape. Now let's really actually prove this result. So remember, we have this Q here. Now this is the extension over B of for all A dash A of phi. Okay. So we can really think of this as the sub-object classified by for all A phi bar. Now, if you remember, phi is just the classifying arrow of R. So phi bar is going to be the transpose of the classifying arrow of R. Now, there's an alternative way to look at what... So I'm going to refer to phi bar as chi R bar for a while, okay? And also, just block your ears up for a second because this is a little bit confusing, but in general sort of notation, according to what McClarty uses at the end of his first chapter on topos, is this Q here may also be called for all A dash R. Okay, that's just to connect with previous notation. Now you can open your ears up again. So the point is that there's an alternative way to think of what this Q is. So like I say, we can think of Q as a sub-object classified by for all A chi R bar. But alternatively, we could say it's the pullback of the name of TA over chi of R bar. Why is this? Well, we know this square on the right is a pullback square. And so the pullback lemma says that this outer rectangle will be a pullback if and only if this left square is a pullback. So we know that the outer rectangle is a pullback because this is the classifying arrow of Q. And so now we know that this left square is a pullback, so we know that Q has to be the pullback of the name of TA over chi R bar. Anyway, what we're interested... Oh, by the way, the way we can visualize this is kind of cool. Basically, what it's saying is that we can write Q as the inverse image of the name of TA under chi of R bar. So remember this chi of R bar, which is also phi bar, is basically picking out some of our sub-objects of A, and this sub-object Q here is the ones that get sent to full sub-objects. So this is the kind of inverse image of this name of TA point under phi bar. But anyway, what we're really interested in is the conditions for a monic S from zeta to B to be in Q. Okay, so let's think about that now. So we have Q, like I say, we can write it as the pullback of the name of TA over chi R bar, or we can write it as chi R bar to the minus 1 operating on the name of TA. And so we're going to have that S is going to be in Q. In other words, S is in chi R bar to the minus 1 of name of TA, if and only if chi R bar of S is in TA. But how could that happen? Well, the only way it can happen is that if chi R bar of S is equal to TA after exclamation mark zeta. Well, the name of TA after exclamation mark zeta. So we can expand this out. This is the transpose of TA P2 after exclamation mark zeta. And so basically we're having our condition is equivalent to saying that these two arrows are equal. Okay. Now for the complicated bit. So, I mean, what we've really got is this, what we wanted to know is the conditions for S to be in Q. And we found that it's equivalent to saying this equation, that chi r bar S is name of TA after exclamation mark zeta. Like this, okay? But what we want to do now is get rid of these transposes. So we use a trick which corresponds to exercise 6.2 in Colin McClarty's book. Now, it's probably easier to go for it algebraically, but I want to really understand everything that's going on. So let's go through it sort of diagrammatically. So we take this diagram here and we times everything by A. And I've got this stuff in red and black here, and it still commutes, okay? Now we add an evaluation arrow, because we've got omega to the power of A times A, so we have this evaluation arrow E going to omega. Now we note that we can compose E after chi of R bar times 1A to get chi of R, and we can compose E after name of TA times 1A to get TA after P2. Now, the next part, we know that composing along here, so chi r after S times 1 is equal to E after chi r bar S all times 1. Okay. But we also know, because of the way that exponential objects work, is we can rewrite this as E of the transpose of this times 1. So we have that this is equal to E after transpose of E after chi r S times 1A all transpose times 1. And then since there has to be a unique arrow, which, you know, doing timesing it by the identity and doing E after it gives this thing on the left, we have to have that these two things are equal. So we have to have that chi r S equals the transpose of chi r of S times 1A. And doing exactly the same kind of trick over here with the name of TA stuff, we get that the transpose of TA after P2 all after exclamation mark zeta is equal to TA P2 exclamation mark zeta times 1A all transposed. And we're positing that these things are equal. In other words, we're positing that these things are equal. So that means that this equals this, and that means the transpose of, or anti-transpose of this equals anti-transpose of this. So our proposal boils down to saying this, and we're basically at home base now. Because what does this mean? Well, what we're really saying is, like, all this reasoning boils down to saying S is in Q is equivalent to saying that this equation holds. And what's this equation? It's chi r of S times 1A equals this thing on the right, which simplifies to T after exclamation mark zeta times A. How can we see that? Well, this thing on the right is TA after P2 of exclamation mark zeta times 1a, and if we just draw that out, we see that it's an arrow which goes from zeta times a, does a load of stuff, then goes to the terminal object. Well, there's only a unique arrow from here to the terminal object, and then it goes t. So it's t of zeta times a. So what's that mean? Well, if we just apply our notion of the sub-object classifier, we see that this is equivalent to saying that s times 1a is in R. So we're actually done with all the reasoning. Now we just need to put it all together. So let's just remember what all this stuff means and we'll get the result we're after. So S is the extension of gamma over these B's. So that's this monic from zeta to B. And S times 1a is equal or equivalent to the extension of gamma over the B's and the A's. And that's a monic from zeta times a to B times a. And R is equal to the extension of phi over B and A. And that's a monic from R to B times A. And Q is the extension of for all A dash phi over these B's. And that's a monic from Q to B. Now let's remember our reasoning. We had that S is in Q if and only if chi R S times 1a is T zeta times A if and only if S times 1a is in R. So what's this mean? Well, basically the point is that S is in Q if and only if S times 1a is in R. So let's now we've basically proved our result, so let's see it. We wanted to prove that gamma implies for all A dash phi if and only if gamma implies phi. So let's see this. Well, we have that gamma implies for all A dash phi. Just doing, just sort of taking extensions, that's equivalent to saying that the extension of gamma over the B's is contained in the extension of for all A phi over the B's. Well, this thing on the left is just S, this thing on the right is just Q. So this is saying S is contained in Q. And we know that that happens if and only if S times 1a is contained in R. Well, S times 1a is the extension of gamma over these B's and A's. So there it is. And R is the extension of phi over these B's and A's. So we have that this holds if and only if this containment of extensions holds, which is equivalent to saying that gamma implies phi. So we're done. Simple as that.